Greetings everybody. Let's kind of pick up where we left off last time and continue on with the fundamental theorem for line integrals. So for the fundamental theorem for line integrals, we suppose that we've got some function f, and f is either a function of two variables for some domain D mapping into the real numbers, or it's a function of three variables for some subset D, and it's a real valued function. And remember that when we had one of these scalar functions of two variables or three variables, then we could compute the gradient of that function and get a vector function out of it. And so if we take and remember what the gradient was, we just take the first component was the partial with respect to x, second component was the partial with respect to y, and the third component was the partial with respect to z. Or if we just had two variables, it would be partial f, partial x, partial f, partial y. The function f in the function little f in this case was what we called the potential function for this vector function, this vector field that we get out of this scalar function. Now, what's really kind of nice about the vector fields that kind of arise as the gradient of some function, we get something that's actually pretty similar to our fundamental theorem of calculus, and really this is kind of going to follow really from that. It's just kind of a generalization of that, or maybe kind of an extension or an application of it. You might want to think about it, but we call it the fundamental theorem for line integrals. And that's if we do the integral over the curve C of the gradient of f dot dr, that just ends up being f evaluated at r of b minus f evaluated at r of a. So basically, if we're taking the line integral over the derivative, then that's just the original function evaluated at the endpoints, which is kind of what we expected, again, a little bit from our fundamental theorem of calculus. Okay. And this is going to work for f being a function whose first order partial derivatives exist and are continuous on this curve C. So we can say, well, exactly why is this going to be true? Well, in essence, kind of remember that we've got the chain rule. The chain rule said if we take the derivative with respect to time of the composition of this thing, then this was really the gradient evaluated at the curve itself times the derivative of the inside. So derivative of the outside, keep the inside the same, times the derivative of the inside. Okay. But in this case, this is really just kind of our dot product now in this case. So what happens, well, we've got the integral over our curve of the gradient of f. Well, what was that dr? It was dr dt dt. Well, this thing was the derivative of f of r of t. And so we are doing the integral from a to b of our derivative. Well, what does our fundamental theorem of calculus say? That's our original function evaluated at the endpoints, namely r of b minus r of a. So this is really just a natural consequence of our fundamental theorem of calculus. Now, an important point that kind of goes along with this is that in order for these derivatives to exist and be continuous, the original function must also be defined at those points as well. Now, we may be just presented with a vector field and we can ask the question, is this thing the gradient of some function? That's a different question than us being presented a scalar field and then computing the gradient from that. And so this will necessarily have implications that we'll see coming up pretty soon. Now, a vector field f for which there is this potential function f, such that the gradient of little f gives us our vector field, is called a gradient field, or it's called a conservative vector field. So an important implication of the fundamental theorem for line integrals, FTLI, the fundamental theorem of line integrals, has to do with loops in one of these conservative vector fields. So recall that for a simple closed curve, r of t, our endpoints, our starting point, was equal to our ending point. And so if we do the line integral of the gradient of some function over the curve C, well, that is our starting point, f of our starting point minus f of our ending point, but that is the same point, and so we're identically going to get this 0. So for a conservative vector field, if we integrate around a simple closed curve, that's automatically going to be 0. And kind of extending that just a little bit, if we had two separate paths from P to Q, sort of two different points, two paths C1 and C2, then remember if we kind of reverse the orientation on one of those paths, so if we do C1, reverse the orientation on C2, then that gives us a loop. And so in particular what that means is that our curve C of C1 plus a negative C2, this is going to be a simple closed curve. And so our integral over C of this thing is guaranteed to be 0, but our properties of line integrals say that that thing we can separate as two different integrals. And for this one, since we've just changed the orientation, that introduces a negative sign. And so what the kind of punchline is of that is the line integral over two different, over 2 points is going to give us the exact same value. So if we kind of move this one over to the other side, then kind of another way of saying that, this property that we get, is that the value of the integral is independent of path. It doesn't really matter how we get there. As long as we get there, our line integrals are going to be equal in that case. And so this kind of leads us to a notion of a vector field F is said to be path independent in an open region D if and only if for any 2 points P and Q in there and any 2 paths C1 and C2 between P and Q, we have that the line integrals are going to be equal. And so now we've got kind of two different notions floating around here. We've got this notion of path independence. We've got the notion of conservative vector fields. And one thing that we're going to be interested in is how do those two properties kind of interplay with one another? Are they the same? Are they not the same? Are there certain circumstances that are the same? And so we'll have that question in addition to maybe one more property that's going to be floating around in the mix, and we'll introduce that one coming up in a video or two. And so I will see you guys at that point next time.